Hello everyone, myself Yadagiri, Assistant Professor, Department of Electrical and Electronics Engineering, MLR Institute of Technology, Hyderabad. So in the last session, we have discussed about the Thevenin's and Norton's theorem, both are the network theorems. So we can use both theorems to get the response quickly for any kind of complex network. So in this session, we are going to discuss about the simple numerical based on the Thevenin's and also the Norton's theorem. So for that, we need to take a simple problem. So that is the network given below. So to get the current through 4 ohm resistor by using the, so we have already discussed it. So by using or by applying the Thevenin theorem, we can simply replace the whole circuit, whole complex circuit into the single source network. That is one voltage source, then the corresponding voltage called Thevenin voltage, and which in series to the single element that's called RTH. So this is the procedure to get the required value in the given network. So this is a procedure. This is the thing we need to replace the whole network into the this simple single source network. So how can we get this simple network from this kind of complex network? So that we need to get the first of all VTH value and also the RTH value. So after determining the VTH and RTH, then we can simply replace the whole complex circuit into the single simple source network. So for that, first we need to go through the the first step, that is VTH, calculation of the VTH. So this is the procedure. First step, the step number one. The step number one clearly indicating us to determine the VTH of the circuit. Determine the VTH. That nothing but the Thevenin voltage. So to determine the Thevenin voltage, so this is a procedure we need to follow. So to determine the VTH of the circuit, we can simply remove the, we can simply remove the load resistor from the load terminals. So in the problem, they have mentioned we need to get the current through 4 ohm resistor. That corresponding element is called as load element. So that we can simply, while calculating the VTH, we can simply remove the load resistor from the load terminals. So previously there is a load between these two. That's why we can remove this element from these terminals. Then only we will get the voltage across. So the voltage across these terminals. That's why we can remove that. So the procedure to get the VTH is, so we need to remove the load resistor and the corresponding terminals are simply keep as it is, that is open as it is. And whatever the voltage appear across the AB terminals, that voltage is simply called open circuit voltage and also called as Thevenin voltage. Open circuit voltage or Thevenin voltage. So how can we get the VTH value? There is a two procedure here. So first procedure, here the 10 ohm resistor, we can simply observe the 10 ohm resistor. So the 10 ohm resistor is connected the open terminal A. So the terminal A is, that is connected terminal A. The terminal A is an open terminal. So whatever the element we need to connect to the open terminal that used to lost their property. The 10 ohm resistor lost their property to oppose the flow of electrons. That's why the 10 ohm resistor is a redundant. So we can simply say that is redundant. So that we can remove that or ignore that 10 ohm branch. So then only whatever the current given by this, so this 16 volt battery or voltage source, that is circulating. So based on this path only. Why? Because there is no element present over the point B terminal, point A terminal. So that's why it's a dummy, acting like a dummy only. So here we can say there is no potential difference between this point to this point, and also so that we can put this point also we can put A, and there is no potential difference between this point to this point, and we also put this point is B, and whatever the voltage appear across these AB terminals are same as this AB terminals. So that's why we need to get the voltage across the 6 ohm resistor. So that voltage same as this AB points. So that corresponding voltage is also called as the Thevenin voltage or open circuit voltage. So here this is the series circuit we have observed based on the current flow. So this is the flow of current to the network. So based on the current flow, this is the series circuit. Then whatever the elements are in series, to get the required element voltage, we can simply apply what? Voltage division rule. So we can apply the voltage division rule. So to get the voltage across required element. At what element we need to get the voltage? Across 6 ohm resistor. That's why according to the voltage division rule, 6 ohm resistor, also we can say VAB equal to, also we can say VAB equal to, that is a total voltage into same resistance. We have already gone through the what are the voltage division rule. Same resistance divided by the total resistance. Same resistance divided by the total resistance. So based on that one, V6 ohms or VAB equal to, so what's the total voltage? 16. What is the same resistance? At what element we need to get the voltage value? That that element is known as same resistance. That's why we can put 6 here. So divided by total resistance means, so whatever the elements are, divide the voltage, then we can, the combination of that element is called simply total resistance. That is a 6 plus 2. This is a 8. 8 is 2. Then we'll get 12 volts. So therefore, the VTH or VAB, we can say, also known as open circuit voltage, is how much? That is a 12 volts. So this is the one procedure to get the RTH of the VTH of the circuit. Also there is a other procedure. So to get the VTH, that is so that is we need to go we need to apply the Kirchhoff voltage law. So based on the Kirchhoff voltage law, there is other method also there to get the voltage across the open terminal, that is so open circuit voltage. So how can we get that voltage value means, so same circuit we can take here. So this is the source voltage is a 16 volts. Now this is the 2 ohm resistor. So this is the 6 ohm resistor and this is the 10 ohm resistor. So this is the point A and the point B here, and this is the 10 ohm resistor. So here the 10 ohm resistor is connected to the open terminal. That's why it's act like a dummy only, means that lost their property. So that's why only one element is only one element considered as, the 10 ohm resistor is considered as a redundant of the network. So now the current is circulating from the 16 volt battery or source, that is this way only circulating. So when we need to get the voltage across, required to get the voltage across AB points. So AB point means, so there is no other element between the AB points. To say this is the dummy, act like a dummy. So this is the point A we can assume, because there is no potential difference between this point to this point. That's why it's also we can say point A. It's also we can point B. So here finally the point is, so we need to calculate the voltage across the 6 ohm resistor. That voltage is known as the Thevenin voltage or open circuit voltage. So how can we get the voltage across 6 ohm resistor means, that is a V6 ohms equal to the, according to the Ohm's law, I into R. So according to the Ohm's law, I into R. Here R is already mentioned. So we need to get the current through 6 ohm resistor. So before going to get the current through 6 ohm resistor, first of all we need to find out the current through network, that is I total equal to the V by R equivalent. So V is the 16 and equivalent is the 2 plus 6, because it's a series network. Only 2 elements are present in the network. That's why 6 and 2 are in series. The combination of that is 8 we can say. So the overall current flows in the network is a 2 ampere. So based on this value we will get the again, so the voltage across the AB points, that is a 6 ohm resistor. So voltage across the 6 ohm resistor is, so that is, so V6 ohms equal to the, or VTH equal to the, according to the Ohm's law, I into R. So in the series network, same amount of current flow. So whatever the current driven by the 16 volt battery, the same amount of current is circulating towards the entire network. That's why the current flow to the 6 ohm resistor is 2 only. So this is the 2 into 6 we can substitute. Therefore, VTH or VAB, so equal to the 12 volts. So whatever the method adapting like simple, then we can choose any method. Both are will get the same thing only. So this is the procedure to get the Thevenin's resistance value. This is the procedure to get the Thevenin's resistance value. Thevenin's voltage value. This is the VTH value we can get either this method or this method. So in the network, so to get the current through 4 ohm resistor, we have determined the VTH. Then we will go through the RTH of the network. So there is a procedure to get the RTH of the circuit. So that is RTH. That is step number 2. In the step number 1, we we have got, that is VTH of the circuit. The step number 2, we need to get the RTH of the circuit. So that is find the RTH. Find RTH. Find the RTH, that is. So how can we find the RTH means, first we need to deactivate to find RTH of the circuit. We need to deactivate the energy sources, which can, I mean, if it is a voltage source, which can be replaced by their internal resistance, actually their internal resistance. So if it is a voltage source, then it is ideal means, so that we can simply replace it by, so that internal resistance, that is a simply short circuit, there is no internal resistance of the ideal voltage source. Then if it is a current source, we can simply replace it by that open circuit, because the internal resistance of the ideal current source is infinity. That's why we can simply replace it by that one is open circuit. Then the corresponding network is going to be appear like this. This is the 16 voltage battery, and this one is 2 ohm resistor, and this one is 6 ohm resistor, and this one is 10 ohm resistor. And along with this one, we also do one more thing, that is we need to also remove the load resistor. Find the RTH. To find the RTH, we can deactivate the sources, which can be simply replaced by their internal resistance, and also remove the load resistor, and also remove load resistor, which can be simply keep as it is. I mean, the corresponding terminals are simply open as it is. Then the equivalent resistance of this combination, this is the point A and the point B. So then we'll get the R equivalent from here. So whenever we had the word as R equivalent, first of all we need to determine the series and parallel combination of network. So based on that, we can connect a dummy source between the AB point that delivers some current. The current is flowing from point A and enter here and divide between these two. So based on this analysis, the current is dividing between the 2 and 6 ohm resistor, and which in series to the 10 ohm resistor. So that's why R equivalent of the above circuit equal to the 2 parallel to 6, which in series to 10. Means R equivalent equal to the, or we can say RTH equal to the, so that is a 2 into 6 upon 2 plus 6. So plus 10 we can keep as it is. Therefore R equivalent equal to the 12 upon 8 plus 10. So we will get, that is 92, because it's a 80 plus 10, 12, that is a 92 divided by 8. So here 4, and we got here 4 and 6, and here 4, and we got here 14. So finally, therefore R Thevenin value of the above network is 14 ohms. So this is the RTH value. So then after this one, actually what is our aim? To find out the current through 4 ohm resistor. We need to find out the current through 4 ohm resistor. So further we have done the VTH value and also the RTH value. Using that two parameter, we require to draw the, so that is Thevenin's equivalent circuit. That is step number 3. Step number 3 in the Thevenin theorem, that is, so draw the Thevenin's equivalent circuit. Draw the Thevenin's equivalent circuit to find the IL value. So this is the Thevenin voltage source, that is a VTH. So the VTH value we got it as a 12 volts based on the previous analysis, and this is the RTH of the network. So this is the RTH. So the RTH value is, so we got it as simply 14 it is. Then, so previously we have removed the load, I mean in the beginning of the network, so we have removed the load always. That's why we can keep, or we can connect the load is at the low terminals. So this is the low terminals. So this corresponding circuit is simply known as the Thevenin's equivalent circuit. So based on this one, we need to find out the current flows through the load resistor. So here, how can we get the current flows through the load resistor? Means we can simply go through the required circuit law, that is Kirchhoff voltage law. We can apply simply. Otherwise, Ohm's law. So according to the Ohm's law, we require to get the current through load resistor, that is IL. IL equal to the V by R. I mean to say, so the current flows through the load resistor I 4 ohms equal to the, so that is total voltage by total resistance, means RTH plus that is RL. So which equal to 12 upon 18. It is a 9 and this one is a 6 and it is a 3 and it one is a 2. So therefore the current flows through the 4 ohm resistor equal to the, so that is a 2 by 3 ampere. So this much amount of current flows through the 4 ohm resistor. That is IL, we can say IL or I 4 ohms, both are same. So this also we can call IL value. IL or I 4 ohms is a 2 by 3 ampere. So that is a 0.66 ampere we will get exactly. So this is the procedure we are applied to get the required value by using the Thevenin theorem. And the second problem, and we need to discuss the problem based on the Norton's theorem. This is the Norton's theorem we can apply. And so this is a given network. By using the Norton's theorem, we can get the current. So in the question they are clearly mentioned, find the Norton's equivalent circuit for the given below circuit by using the Norton's theorem. So we need to get only the Norton's equivalent circuit. The whole network simply can be replaced by, it's a complex network because we have the many independent sources and also many passive networks. Passive elements. That's why we can simply replace the whole network with the single current source and which parallel to the single resistance. So this is R Norton and this current source is called I Norton. So we can simply remove the, we can simply replace the whole complex network into this simple Norton's equivalent circuit. So for this, first we need to go through the procedure to get the IN and also the RN. Then we will draw easily the whole complex network into the simple Norton's equivalent circuit. So for that, first of all, we need to go through the IN value. That is the step number 1. So the step number 1 clearly indicating us find the IN value. So how can we find the IN value means? So to determine the IN value, to determine the IN value, so we can simply remove. We can remove load resistor. We can remove the RL and which can be short circuited. And the corresponding terminals are going to be short circuit. So here there is no load element. We need to get the Norton's equivalent between the AB points. That's why. So there is no load element removal required. That's why we need to simply the same circuit we can take for this step. So that is here 2 ampere current source, and this is the 4 ohm resistor, and this one is a 12 volt voltage source, and here there is a element connected, that is a 8 ohm, and this one is also 8 ohm, and this one is 5 ohm. So these two points are AB points. So we can simply short circuit these two terminals or these 2 points, because so we need to get the INR ISC value. We can simply short circuit the required terminals, load terminals. So this short circuit path. So whatever the current flows with the short circuit path, that is called a Norton's current or short circuit current. So this is only we will get from this one. So for this we need to do circuit technique. We need to apply some circuit technique. That is here one current source is present in the network, and here there is a voltage source. So we need to transform the required voltage source into the current source by using the source transformation technique. So based on that, so this branch current value equal to that is a I2, and we can say I2. So the current source present in the network, that is a I1. So then the second one is I2 equal to, then formula V by R equal to Ohm's law only. The source transformation is a method. So to transform the one kind of source into the another kind of source, that is a voltage source to current source, and also the current source to voltage source based on the requirement. Here there is a current source present in the network, and in series to the one independent, in series to the one resistor, that is a ideal voltage source category. This one, I mean to say, there is a internal resistance present in series to the voltage source. Then we can easily transform the network. That is the source. So based on that one, we will get the 12 upon 4, that is 3 ampere. So we can redraw the network. The 2 ohm element is key capacities, sorry, 2 ampere element is key capacities, and instead of this whole branch we can simply replace it by current source. So that is one more current source with the same polarity, that is a 3 ampere based on this value. So that is a 3 ampere. So previously there is a internal resistance present to the voltage source which is in series to that source. So in this case that is comes to the parallel mode. I mean this is the parallel of 4 ohm resistor. This is 4 ohm. So then the remaining elements are key capacities. This is the 8 ohm and this is also 8 ohm and this 5 ohm, and these two terminals are short circuit terminal. We can say A and B. So this current is short circuit current or Norton's current. So we need to find out the current through this branch. So for that we need to do some reduction. So because both are the current sources both are current sources having the same polarity, that's why. So we can simply add the current sources, I mean which convert into the single current source network. So that is, so this is the current source. So the combination of these two, both are having same polarity, we can simply add them. That's why we will get the 5 ampere source, and this is 4 ohm branch element. So this is the 8 ohm branch, and this is the one more 8 ohm branch, and this one is a 5 ohm branch. So this is the short circuit terminals. So that is the AB points. We require to get the current through this terminals only. So this is the 8 ohm resistor. So this is 8 ohm resistor. So here we need to get the current through AB points. So how can we get the current through AB point? Means first of all we need to find out the overall current of the network. So there is a procedure to get the overall current of the circuit. Actually if it is a voltage, then we will go through the procedure. So but the network having the current source itself, we did not go through again calculate the current value. So this 5 ohm only circulating towards the internal network, and also that 5 ohm only coming to the AB points. So the current is coming from 5 ohm resistor like this. This is the current division path, then divide between these two and again enter here. So instead of the current division between these two parts, whatever the current coming from the 8 ohm resistance, that directly moving towards the AB terminals only, I mean short circuit path only. Why? Because so it is appear nearby or parallel to the short circuit branch. That's why it is comes under the redundant. So I mean the 5 ohm resistor is lost their property to oppose some amount of to oppose the flow of current. So that's why we need to ignore it, this 5 ohm branch. So that we need to find out the current through this element. Then here we are apply current division rule to get the ISC value. ISC or IN equal to the, so total current of the circuit into then opposite resistance, because we are applying the current division, because the current division is taken place. That's why. So we are applying the current division rule, opposite resistance by total resistance. So that equal to the total current is a 5 ampere, then opposite of the 8 ohm, because 8 ohm only connected towards the short circuit path. That's why need to find out the current through this 8 ohm branch. So opposite of 8 ohm is only 4. 4 divided by the, then 4 plus 8 plus then 8, because one more 8 also there. So whatever the current circulating towards the 8 and also AB and also this 8, that is called I Norton or short circuit current. So this value is 20 divided by the 20. We will get, that is 1 ampere. Therefore, so the Norton's current of the circuit should be 1 ampere. So this is the procedure. So to get the IN value. So then in this one we have done this one. Then we need to get the RN value. So this second step, that is step number 2. So that is find the R Norton. Find the R Norton. So to determine or find the R Norton, to determine the R Norton. So whatever the procedure we have followed in the Thevenin resistance, so same procedure we need to get. We need to follow to get the RN value. That is, so remove the load resistor. Remove the load resistor from the load terminals. From the load terminals, and also deactivate all energy sources. All energy sources. I mean, if it is a voltage source, we can simply short circuit. If it is a current source, we can simply open circuit. Same only we can follow. So in the network, we have the different kinds of sources are present. That is, so that is one voltage source is there and also one current source is there. So here there is a old current source, so that we can simply open circuit. Here there is a element is a 4 ohm, and this is the, I mean, these points are, I mean, these 2 points are indicating us there is a presence of the voltage source. Then we can simply short circuit these two. And this is the 8 ohm resistor, and also this is a one more 8 ohm resistor, and this one is a 5 ohm resistor. And these 2 points are AB points. Here we did not do the short circuit because these are low terminals. Simply while calculating the RN and RTH, we can simply keep as they are open as it is. So this is the open circuit. Instead of current source, we can simply keep open circuit terminals. Then whatever the resistor value we will appear between the AB points or open point, that is called RN. So that is, so based on this one, the current is given by the dummy source from the AB points. So that is circulating like this, and divide between these two. Based on this one, 8 to 4 8s are in series. Therefore, RN equal to the 8 plus 4 plus 8 is in series, which is parallel to 5. So we will get that is a 20 parallel to 5. So according to the RNR method, the Norton resistance value equal to the 20 divided by the 4 plus 5, 4 plus 1. So that means 20 upon 5. So we will get directly 4 ohms. So therefore, Norton's resistance value from the above level is a 4 ohm resistor. I mean 4. That is a 4 ohms only. So using these two parameters, we can determine or we can draw the, so that is Norton's equivalent circuit. The step number 3, that is draw the, so Norton's equivalent circuit by using the Norton's circuit parameter, that is IN and RN. So this is the IN we got. So that is a 1 ampere. We have already determined that is, and which is in parallel to single resistance, that is RN equal to 4 ohms. So this is the required thing. So this is asked in the this question. So in this question, they have asked find the Norton's equivalent for the network by using Norton theorem between AB points only. That is, so these 2 points only. So at these 2 points, we'll get the, so this circuit only, that is Norton's equivalent circuit. So this is the end of the session. Till now we have discussed in this session. So the problem based on our numerical based on the Thevenin theorem. So in that, how can you get the, or how can we find out the Thevenin resistance and also Thevenin voltage source, Thevenin voltage value. So based on that one, how can we get the required value, required parameter value, that is the required current and required voltage, that is load voltage and load current. And also we have derived, I mean we have also solved the one question based on the Norton's theorem. So in that we need to get the, how can we get the Norton's current value and how can we get the Norton's resistance value. So that we have discussed in this session. So this is the end of the session, and the coming session, I mean in the next session, we need to discuss about the maximum power transfer theorem and also the numerical based on the maximum power transfer theorem. So this is the end of the session, and thank you one and all.